just a few questions to get to know you a bit. How many of you do you currently use SQL systems, SQL in your systems, in some way? All right, so most of the audience. How many of you actually tried, using or trying to look into big data technologies? All right. So I'll explain about this talk in just a few minutes. Before that, I was told to tell you you can ask questions via some Slido app. If you have it, I have it here. I'll look at it. But also don't be shy to just raise your hand and ask any questions even during the talk. That's perfectly fine. Don't be shy. So this talk is about SQL. It's about big data, but it's not going to go the way you think it is going to go. I'm not actually going to talk about SQL as SQL and structured query language and tables and rows and everything. I'm going to show you how to use the tools that you currently have or currently use in your systems. Basically, SQL is something that is very common for reports, etc. And I'm going to show you via some user story we had how you can still use SQL and even Python programs and everything against data structures that look like tables, but can actually operate on large amounts of data, and hence the wording big data. And we'll discuss this in just a few minutes. My name is Itamar. I'm the owner, founder, and CTO of a company called BigData Boutique. We basically deal with a lot of big data projects. And by big data, I basically mean, again, projects that have some challenges with the amounts of data, of ingestion or data at rest, those kind of projects, as well as some cloud projects, moving data centers to the cloud and improving cloud usage, etc. And we are acting as partners of several software vendors. Elasticsearch is one of them, and we are going to also look a bit about how to use Elasticsearch to do those things that I'm going to show you. So we are going to discuss a very special problem, a problem that basically data is all we have, and what actually makes up our companies, or what makes our companies worth quite a lot of money a lot of times. And that while this is a very positive thing, it also gives us a very big, a very interesting challenge. And that is usually because of the amounts of data that we need to have in order to be successful at our mission, whatever our mission is. And those amounts of data will actually make it a bit harder for us to work or to scale and to move forward. So when I talk about the data problem, I talk about a lot of challenges with BI, business intelligence software. So do you have business intelligence software in your organization? If you don't, well, maybe you should, and you'll know how to improve on your organization. If you do have it, do you actually use and do you collect and do you use all the data that you can possibly collect and use? How long is your retention period? Are you deleting data because you just can't accommodate all of it, or because it's just costly? Do you currently, maybe you don't have a strict retention policy and you can actually collect and store all of the data, but does that data grow? It probably is, and once it grows, can you actually accommodate the growth? So a lot of you, like you said earlier, a lot of you actually currently use SQL databases for that, or use SQL query language or on something else. So you currently probably have it, but are your users also have it accessible to them? So they can execute SQL queries, but can you do machine learning algorithms on your data? Can they write some more sophisticated code like Python programs, R programs, against your data? So all of those are challenges that we will actually have a look now today. And it doesn't necessarily have to be on the big data area. So I'm not going even to discuss what big data is, right? I mean, it doesn't really matter. As long as you have amounts of data and you want to make use of it in a way, this talk is for you, and I'll show you how you can make it better in your systems and organizations. So this is actually a story of a project that we did several times with several clients, and I'm going to walk you through the process of how we usually do it. And we made up some company name. The use case is quite similar to one use case we had with one customer. And once we went through the process and I showed you the challenges and the process that we go through, we'll talk about technologies and how to actually use them and what they can give us in our process. So this is a company, let's call it adbidding.com. Adbidding.com is a company that allows advertisers to show ads in a lot of websites, right? So it has two kinds of customers. It has the kinds of customers that want to put ads somewhere, and it has customers that allow it to put ads on their website. So two types of customers, and that brings basically a lot of entities to the table. So for the basic entity you would think of is just an ad and a place to put the ad on, right? So a publisher website and something like that. Now, those two entities have a lot of entities on top of them that will make ad bidding make ad bidding happen. So a bid request, an ad request, a bid, an impression, a click, etc., etc. So take that for static image ads. Add a lot of more further events on top of that. So, for example, video ads and stuff like that. How long the period that the video was watched, etc., and what timestamp the video got clicks on. This basically gives you a very big amount of events and event types and entities in one system. So there is some algorithm that takes care of all of those entities, but the customer actually wanted to be able to make sense from all of that data and create reports. So those reports are sometimes offline reports. So you have analysts, they sit in a dark corner, they type a lot of SQL and what have you, and they want to generate reports to understand how the business is going. But there are also other types of reports. Those reports are reports you want to show to your customers on some backend screen, or you want maybe to email them and to alert them that something happened, or just daily emails with reports. So there is offline reports and there is online reports that you want to generate ad hoc as the system goes, and then your customer can log into the system and actually request a very specific report. And that report is something you didn't envision beforehand on design phase. So you sometimes have reports that are very specific and repeat themselves on some time frame, and then you have reports that you would never guess what that report would be. So all of those kinds of reports is kind of built in the system today, and it's built on top of SQL. So SQL Server in that case was a very big database server, and it received all of those events, all of those entities back in the day, and the customer wanted to be able to still execute all of those kinds of reports, basically SQL statements, and still get all the online, offline reports, ad hoc reports, all of those kinds of reports like he did before with SQL Server, but still wanted to maintain that. So reports would look something like that, maybe sometimes with more graphic interface, but you can imagine how a report looks like. So what was the problem? The problem was that they use SQL Server, a single SQL instance with replicas and all, but once they started to grow and started to be successful, the amount of data they collected just got bigger and bigger. If that wasn't enough, they were about to launch a new product, a new, feature or something like that, and they actually saw the amount of events going way higher than they have now. So the current data, the amount of data that they are currently collecting is already almost too big for their SQL Server, and they were anticipating to have a couple of times more than that in just a short period of time. So growing the SQL server to be bigger or go to a cloud deployment of SQL server, that's all just patches, right? Once you start growing big and maybe even get to exponential growth, this is where you need to stop for a second and try to see whether or not your approach is correct, and maybe you do need to redesign or rethink your approach. So that was the point they were at. And they actually had pains already. SQL, because it was so big at that point, some reports would have taken forever to run. SQL can do this to you sometimes. And at some point, SQL will just won't be able to hold all of that data, and they had to find alternatives. So after a lot of discussions with the customer, we got to this short paragraph saying what the goal is. And in this goal, you'd find words that look very familiar to some of you. So they wanted to create a data warehouse. We want to just create a place where we can throw all our data and just query that data. Right, but so that paragraph, reports and dashboards and everything. So that paragraph really sums it all, but we had to drill down into the requirements and find the bullets, the actual bullets that we needed to implement. So to start with, because we know the project and the company are going to grow in a very high rate, and they already have a lot of data coming in at every given time, we knew we had to support high ingestion rate, meaning we have to see a lot of data coming in and be able to just ingest it all without delays. That's the first requirement. The second requirement is, and it's probably the biggest one, it's to be able to support all the type of reports the company currently has. So like I said before, we had offline reports, which is probably the easiest one to achieve, because whatever query you submit, you don't care when it returns, right? I mean, you just want the report at some point in time. But some reports are actually ad hoc queries, meaning you don't know what the query is going to be beforehand. And not only it's ad hoc, you actually want the report to return in a timely manner, right? So even if it takes 10 seconds, 30 seconds, still you want it to return in an interactive manner. So designing the reports, designing the technology behind the reports on basic user queries is going to be the biggest task there in the project. And then another requirement was to support a long data retention period. So right now they had to start deleting data, all data from their SQL system, for the live system, in order to support current data or data that is more recent for most of the queries. They had to do this trade-off. They ideally wanted to avoid that. They just wanted to keep all of the data, or at least data for several years, before they had to remove it. So a lot of customers would actually also ask you to make sure the costs of the data warehouse are low. So they don't want to pay a lot of money to keep a lot of data and to support lots of queries. That wasn't a requirement for that specific customer, but this is also a requirement you'd usually see. So does the storage that you're using, is it a hot storage? Is it something that costs a lot of money? It's a cluster of servers that you have to support. Those kind of questions are really important. In this case, we didn't have that requirement, although we tried still lowering costs, and we'll talk about that in just a minute. And obviously the most important requirement was, do whatever you do, just don't hurt production. Don't disable features, don't take the system down on purpose or not. Just don't hurt production. And we had to do all of that. So we basically had to plan everything to do it as a side-by-side development story. So we started a process. We started working with the client, like I told you, on requirements, and then we had to start understand what technologies to use, how the process is going to look like. So the first thing we did is to establish a common language between all the parts of the company and between ourselves. When the customer talks about an ad, what does he mean, right? When we talks about a log event, what type of a log event? How does it look like? What is a report? Is it an online one? Is it an offline one? We had to establish some common language, so we're able to really deliver and really understand what the the project and what the system looks like. So we mapped a lot of business entities into the technical entities, and again, we speak a different language because we're just consultants. So we had to really map it, and we did that. And then we started plotting the flow of the system and how the data looks like, and the types of reports they had, and each report will touch on those entities, et cetera, et cetera. So we really had to understand specifically what the system does and what the users expect. And for example, one of the biggest questions we asked on the reports is, does this report require some sort of SLA? Does it have to return within a certain amount of time, or can we maybe find ways to, take it easy? So, for example, if a report could have be sent once a day, we don't have it to run it on a system that returns it in real time. We can just run some sort of a job, and whatever it returns, it returns. So we had to really understand that. Identify current and future bottlenecks, and again, to make sure that the customer is satisfied, or in any other company use case, to make sure that you deliver on your task, you really have to understand what bothers the various users, and who are your users, and in a different word, stakeholders, the people who are actually care about the projects that you currently work on. So who are they, what's bothering them, and then what path to optimize for. So again, do you need to deliver on cost optimization, or on performance, on retention, et cetera, et cetera. So we also accounted for the team, the company's team strength and weaknesses. What do they good at? Do they know to even the programming language they use? If we give them a solution that is based on Python, will they be able to actually interact with it, use it, or is it going to just lie there with untouched for several years now? So we did all of that process. We went into several design meetings, and we took our time, and we came up with a list of insights. And those insights are very important for any data pipelines project, for any data engineering project, for any project that actually is going to deal with data and will allow to do the things we're talking about now. So in this specific project, and probably in most other projects that deal with time series data, on events, on data that comes in, and then you want to create reports on that, all right? So all of that data, we identified it to be events. So a piece of data that comes into the system reports basically on some event that happened in the world or in the system, and then can be persisted. So all of that data for that specific customer, and for many other projects as well, we identified that to be a simple stream of events. So we had multiple streams, but every one of them is just a stream of events. Because of that, because it just reports on something that happened in the world, we can assume that to be immutable. And once you can assume a stream of events to be immutable, so it never changes, you can basically do a lot more than you could have if it was mutable, if it had to change. So that is that's probably not entirely true, not for this project, not for many other projects, but as long as a very high percentage, 95% of the data is actually immutable, you can take this assumption and stretch it, because when you will need to fix some data, I'll show you that in a minute, you will have tools to do that. But if you can assume that most data is immutable, take that assumption and stretch it as much as you can. And so that was the first assumption that we had to make. The second assumption is whether or not we can denormalize data, or is the data we're working on normalized or not. So normalized is the type of data that you have lying around in many different places in SQL. It's many different tables, and when you read it, you have to join things together because some parts of it changes, some parts of it won't, and stuff like that. For stream of events, some cases you can assume that you can denormalize data, basically bring all the reference data into that event and just persist it as is. We usually call that point-in-time view of the data within the event. Sometimes you can assume you can do denormalization, sometimes you can't. And this is a very important assumption or a requirement that you would have to work with. As long as you can assume denormalization, maybe the data storage will take more because the data you actually store per event is going to be larger, but you'll be able to do much more because you'll have to do less joins when you read it. But it also requires you to make the assumption of if something changes, if the reference data changes, do you actually have to propagate that change to the event, or you are going to do, or just leave it as is because, again, it represents a point-in-time view of the event, of the data. So, again, that's a discussion you have to have with your stakeholders. In our case, we assume complete data denormalization for the entire data. And we identified 3 types of queries in the system. So there was those online queries that we had to support, and we'll talk that in just a minute. But most of the queries were pre-programmed and daily tasks, daily jobs that we could have run, or some queries that we maybe had to provide to the user once they submitted it, but we could have taken our time on that. So, for example, we agreed with the customer that some reports, the customer could have gone to the backend, put his query, submit the query, and if it takes more than 20 seconds, you just show him a message saying, well, this query takes longer than expected, we'll send the result back to you via email. Okay, so that's a business decision the client had to make, and basically they agreed to, yeah. Here. Sorry about that. So the customer basically agreed to that, or said it's something that they could work with, and we took that as a easier requirement to deal with. But still, we wanted to support some real-time queries as well. So before actually talking about technologies and deciding with the customer what the technologies are going to be, we had to also have a discussion with them about the trade-offs of some queries. And this is where this talk becomes a bit more technical. So when you have data, right, what doesn't matter, big data, not big data, when you have enough data and you want to query on that data, you'd have to find the balance between different trade-offs, between different vertices. So first, the first thing you have to consider is what query language you want to support. So some query languages are very easy to use. For example, how many of you have seen Kibana before? All right, so quite a lot of you. So Kibana is some sort of a query language, right? You just click, point, drag, drop. You get to a point where you just create a query using visualizations, right? There's more lots of tools like that, but the idea is the query language is very, very flexible. It's very easy to use, and it's ad hoc, right? You can't think beforehand what the user could query. So that's an example of a very simple query language that you can offer to your customers. On the other side, you have query languages like programming languages, right? You can write Python scripts. You can write all of those queries that are essentially programming languages on your data. In the middle, you have SQL, which is some programmatic, but a lot of people know it, and it offers quite an easy syntax to understand and comprehend. So the types of queries, the query language that you're going to use, and the types of queries you will allow your customers to perform, whether it's hard-coded or something that they have flexibility with, that's one thing that you have to consider and when you go to decide what is the technology you're going to use. The other vertex is going to be on the query execution time. When you have this query built and you are going to execute it, how long is it going to take to execute? Is it going to take days? Is it going to take hours? Is it going to take minutes? Or is it going to take seconds or milliseconds? Okay, so some queries are okay to take hours, maybe minutes. Some queries cannot take more than 10 seconds. And you will really have to find the balance between the two, because a lot of time the more flexible the query is and the query needs to be, the longer it's going to take to execute that query, depending on the technology, but that usually holds. And then we have the results accuracy. When you actually get a response back, is this an approximate answer, or for example, if I wanted to average a large number of integers, is this going to be an approximate, for example, using algorithms like hyperlog and stuff like that, or is it going to be an accurate answer that you actually go and take and use for billing to actually, I don't know, charge the customer amounts of money to the cent? All right, so all of those vertices are vertices you have to take into account, and those are trade-offs you really have to look into. And the last point here is compute power. So when you execute the query, how much compute power do you need? Is it a hot technology? Is it a cold technology? And if you require a certain amount of compute power and you don't have that compute power currently in your system, you didn't scale up enough, what happens to the query? Does it run forever, or does it just cancels and returns back not enough resources, error, or something like that? So all of those are things we had to show to the customer and discuss that with them to show them what the possibilities are. And we came up with this plan, and that's quite a standard plan for a data warehousing solution on the cloud. So we were using AWS in this case, and we are going to go through this plan together now. But the point is, we decided to store the entire data instead of SQL, which is a hot system that allows you to execute SQLs, etc. We stored everything on S3. S3 is a blob storage by Amazon. It's highly available, and it has a lot of APIs that let you access data very, very efficiently. And we use some technologies to make it even better. And I'm going to show that to you now. The gist is that we took the data and we put it in S3, and we allow different technologies to access it in different ways to satisfy different query strategies. So data warehousing on S3 was chosen in this case and in many other use cases because first, it's cheap. Second, like I said, it has a lot of APIs that allow you to query data very easily, and those APIs are internal to S3, like S3 Select, which allows you to execute SQL on S3. And then you have a lot of other supporting technologies, which I'll discuss now, that allow you to use the data stored once in many, many different ways. To put the data in, we used AWS Kinesis. Has anyone ever heard of AWS Kinesis? Okay. Have you heard of Kafka? Okay. So Kafka is a queue system, but it's not really a queue system. It's more of a commit log, right? You write the data in chronologically ordered, and then you can read it multiple times from many consumers. So AWS Kinesis is just a hosted Kafka, and it allows you to do just that. It supports ingesting a lot of data, tremendous amounts of data into a single queue with many partitions, shards, and then it allows you to subscribe many consumers to read from that queue. Now, once a consumer read from that queue, a message from the queue, that message is not deleted, and you can always go back and reread the message or the messages starting in a certain offset. And that allows you to do a lot of interesting things, not the point of this talk, but using Kafka or AWS Kinesis is really easy to get started with, and also allows you to do a lot of very sophisticated strategies to read the data, update data, recompute statistics, and things like that. So we used AWS Kinesis as the entrance point. And we wanted to take the data from AWS Kinesis into two places. The first one is S3. We wanted to persist it, and I'll talk about that persistence in a second. We also wanted to push that data into Elasticsearch to support some real-time analytics, some real-time aggregations and dashboards for some of the users. So AWS Kinesis, because it's such a queue system, it allowed us to subscribe several consumers to it and do just that. We had data coming in, and all the producers, the web application, the backends, all the workers, everything just pushed data, all the different entities into AWS Kinesis, into that queue system. Then we subscribed 2 consumers into it. The first one would have taken data into Elasticsearch, did some transformations, because in Elasticsearch we had to have the data in a certain way, denormalized in a certain way. And we had it in Elasticsearch to perform some dashboards and real-time analytics. And then the other consumer took the data from Kinesis and pushed it to S3 for persistence. That was the raw data with some transformations, but it was the raw data, and that was the data that we are going to persist for as much time as we can, and also execute more sophisticated queries on. So I'm not going to go into that, but those lines that I just drew, so how do I take data from Kinesis or Kafka to S3? How do I take it from Kinesis or Kafka into Elastic, etc., etc.? This is what we call ETL tools. Okay, so ETL tools are tools that you have so many in the market, and you can just pick and choose from so many different kinds of tools and products. Some commercial, some are not. There's way too many. This is why I'm not going to go into every specific one, but I wrote the general ones, or the ones that you probably want to have a look at in this slide. We in this case, we picked Spark streaming, and we did a lot of work with that. In another projects, we picked Airflow. Really good technologies, but it all boils down to what your customer, again, is going to feel comfortable with, what they can maintain, and what types of inputs and outputs each of them can support. So going back to S3, we didn't just take the data and put it as is. Let's assume we got the data as input in JSON format. We could have actually put the data as is on S3 and just let it run with it. The problem is that if you have data, just raw data on S3, there is lots that you are missing. If you go and start using dedicated file formats like Parquet that I'm showing here, like ORC, Avro, so you get both schema enforcement and a lot of optimizations on top of that. So instead of just storing raw data on S3, you can go to what we call a columnar format. So you start persisting data in files that are built in a certain way that you can compute and select from and do a lot of really sophisticated queries on in a very efficient way. So Parquet is a columnar format with 2 optimizations. One is called projection pushdown, and one is called a predicate pushdown. Basically, whatever query you're going to submit on those files, the query itself is going to go into the bits and bytes and select the pieces operate on pieces of the data that you specifically requested, and therefore it will not pull the entire files out of the storage, but it will be able to operate on them very close to the storage and basically really make high performance queries on top of that. So we did our investigations. We found out that Parquet for those cases is very optimal, and we just went and persisted all of that data from Kinesis into S3 in Parquet file formats. To do the parqueting parts, again, we use Spark streaming. There is other tools. You can do this in other tools as well. But using Spark is a lot of times easier because you have a lot of libraries and integrations that are already built for you. In some cases, we used EMR, which is just hosted Spark on AWS. In some cases, we launched our own Spark clusters. And then we took the data from Kinesis into Parquet files on S3 using Spark. Now, not only we persisted the data using dedicated file formats that let us do a lot of performance optimizations because of the file format, we also use the technique that's called partitioning on S3, and it looks like that. We assume the partition, and a partition can be the file type or the stream type, which in this case, for example, add views, and that's a partition, right? If I'm going to write every different stream into different buckets in S3 or different prefixes in S3, that's going to be a partition. But then we also partitioned on the timestamp, on the date and the timestamp. And this so-called folder or prefix looks a bit weird, right? You write the field name equals and some value, but that type of partition allows you to basically push down the predicate or the query that you wrote on some field into, again, the storage system itself. So the execution engines for the queries that we're going to discuss in just a minute will actually be able to understand that you're only querying parts of the storage system because you basically specified the values, you put them in the path of the storage system itself. It looks like a folder in S3, we actually call it a prefix, but the idea is the same. You can tell the execution engine not to query a lot of partitions and only go to certain partitions based on the query. So we used Presto for most of the queries, and luckily for us, Presto was able to satisfy a lot of the requirements we discussed. Presto is a really nice technology built by Facebook and open sourced a few years ago. It's actively developed and getting a lot of traction recently. So it knows to connect to a lot of data sources. So HDFS, S3, and many other storage systems like that, that's a given. But it also knows to connect to traditional SQL servers and MySQL and Oracle. It knows to connect to NoSQLs, Cassandra, MongoDB, Redis. I think there is a Couchbase support as well. And also other types of systems like Kafka. Presto does that using what we call a connectors. Connectors in Presto basically define the connection between the execution engine, Presto, which knows how to deal with tables and rows. This is the language that Presto speaks. And those connectors map between the underlying data sources, the concepts of the underlying data sources, to Presto itself. So mapping between SQL, like MySQL, and Presto, that's trivial, right? You just map SQL to SQL. But mapping between NoSQLs to SQL, well, that is the connector's job to map between a document and fields into a concepts of SQL, and that's what those connectors do. Now, Presto is able to take those data sources and that transformation into the SQL tables and rows language and execute very sophisticated queries, including what I just mentioned, projection pushdown, predicate pushdown. So Presto is able to optimize queries, whatever the data source it is executing against. On top of Presto, we can connect pretty much every BI, every SQL, every tool that supports SQL. Presto supports JDBC drivers, so basically pretty much any tool nowadays knows to connect to a database, so-called, with JDBC support. So JDBC driver, Presto has a JDBC driver you can use, and that allows you to connect Presto to all kinds of dashboards like Superset, Redash, Tableau, tools like that. And you can also connect to it with your programming languages, right? You can just write code against a JDBC driver, pass it some SQL, and it will execute. Presto is a distributed system. So you launch several nodes. One of them will act as a coordinator. It will accept the queries, and it will run them and make sure that all the other nodes are going to execute correctly. If one node fails, it knows how to pass the part of the query that that node handled into a different node, etc., etc. So that's an execution engine. It's quite similar to what Spark does, for those of you who are familiar with Spark. The difference between Presto and Spark is that Presto is a real-time or interactive query engine. You submit a query, and you should expect the query to return within seconds or dozens of seconds, not more than that. Unlike Spark, which knows to get a job, even if it's SQL or some sort of a program, it will execute that job, but it will finish when it's finished, right? Sometimes it will not finish and it will crash and you will not even know, but that's a different problem. With Spark, jobs will run however as much as they need to run. With Presto, there is no such thing. Presto will actually, you can configure it to kill queries if they take more than X seconds. So Presto is a really, really nice technology, and it shows you exactly what's going on with really nice UIs. So you can see that standard SQL is being executed. We can see in real time what's going on in the system. We see how many workers work on that, how much data was loaded, how much memory is being used, and stuff like that. And Presto really helped us achieve most of the querying requirements that I showed you earlier. So for online reports, Presto is the perfect choice, right? I just submit the query, and the user submits the query from the backend. I pass that SQL, I create an SQL statement, which was already what that specific customer had before because they used the SQL server. I pass that SQL to Presto using the JDBC driver, wait for it. When it returns, I just show the results back. All I have to do is maintain the Presto cluster to make sure that it is operational, it has enough resources, it doesn't crash, it's available, and so on and so forth. On AWS, we have AWS Athena. How many of you heard of AWS Athena? Okay. AWS Athena is just a hosted Presto. Okay, so AWS took Presto, a great product, and just hosted it. They do the maintenance, they make sure they have enough compute power, and what you basically get is an endpoint you can submit queries to, you get back results, done. There are a few issues or missing features with Athena. Some of them relate to the amount of data sources you can connect to. So Presto can connect to a lot of data sources. AWS Athena is a lot more limited. It uses AWS Glue and things like that. So you can connect to a lot fewer data sources, and more limitations in the query language and things like that. But the developers of Amazon that work on AWS Athena are actually Presto contributors. So you can actually you see them active in the open source community of Presto. So they are quite close to the table, and eventually I assume AWS Athena will become better and better. But that's a hosted Presto. For some customers, we had to deploy Presto ourselves. I'll share the link to how you do that in the end of the slides, but basically not too hard to pull off. On top of Presto, we put some dashboards. What I'm showing you here is called Redash. Really, really great dashboard. And Redash can connect to, again, many data sources on its own. So you can connect Presto to execute SQLs on multiple data sources. And by the way, I didn't mention that, but you can also join between different data sources. So you can execute one SQL with select from MySQL, select from S3, select from Kafka even, and then join the data together on Presto within a single SQL statement, which is really cool. We use that in several places. And Redash lets you build dashboards on top of any JDBC connector whatsoever, and some other connectors as well. So we use it, and it was really, really nice to do. We also use a lot Jupyter notebooks. and similar to that is Zeppelin, which allows you to write, again, SQLs, but also code like Python and Scala against your data. And we use that a lot as well on top of that data that we store on S3. Some tasks that we execute are not good enough or are more sophisticated than what Presto can support. So we really had to find a way to execute long-running tasks, machine learning tasks, or like big reports and stuff like that that SQL just couldn't satisfy. Or even if we could have used Presto, we should have used a lot more compute nodes for Presto, and we opted for running this a bit slower overnight, for example, using jobs that run offline. And that's what Spark is for. So we had a Spark cluster. We use Spark for parqueting, like I mentioned before, to take data and process it to be on Parquet format on S3, but we also use Spark for a lot of long-running jobs and nightly jobs that compute data and produce reports and found outliers and things like that. Also, you can expose Spark for HTTP requests using libraries like Livy, so you also have the option for that, but we mostly use Spark for scheduled jobs on top of the data. The nice thing about all of that, I'm going back to this map, the nice thing about that is that both Spark and Presto are going to use exactly the same data on S3. So you compute the Parquet files and the persistence once, you create it once, and then you can query it multiple times from many, many different sources. Elastic in this case is not going to use that S3 bucket, but it would have to use the data that's coming in real time directly into Elastic for real-time analytics and dashboarding. We also, a bit short in time, so I'll just skip of that quickly. We also use Elastic to monitor the entire process, right? So how do you know if your some Presto jobs failed, some Spark jobs failed? You really have to monitor that, and we use Elasticsearch and Kibana for that as well. What I showed you now, we were able to pull a POC within 3 days because it's AWS APIs mostly, and because we use Terraform with many pre-made scripts. So it was really, really easy to get going with, and that's how it looks like when you do things on the cloud. Some gotchas. So there are a lot of many small things in this area of technology where you really have to either notice in advance or deal with it as it happens. For example, don't put small files on S3. That's really, really bad for you. Spark really hates to pull so many small files when it does its computations. Presto is not good at that. You'll pay a lot for API calls to S3, things like that. So also when you do parqueting, when you run the job for parqueting, you usually have to do this on a two-phase. You have to run once from Kinesis into an intermediate bucket, and then from that do a further compression on a daily basis to make this even more storage optimized. And Kinesis sometimes gave us some issues. So some really small gotchas, but for the POC, it's really, really easy to get started with. There are a lot more challenges that I didn't discuss here. For example, how do you find the ultimate partition size, the ultimate file size, the compression type? How do you deal with data corrections? So, like I said, we assume the data is immutable. What if it doesn't? What if it isn't? Right? Do you still go that route? Do you correct the data every now and then? How fast data corrections should appear in your data? How do you deal with schema changes? How do you deal with monitoring? So a lot of topics I didn't cover, but they are there, and you really shouldn't ignore them. Those are links to Terraform deployments of Presto and Elasticsearch on AWS, Azure, and Google Cloud. It's really, really easy to get started with. Go and use it if you want. I have like 1 minute left for questions, and I'll look at that up. But if you have any questions, just shoot. Yeah.
So what's the main
Mostly costs, because any document DB will basically be a hot storage, right? You will pay so much more, but also for the types of computations you can do and the speed at which those queries are going to run. So if you try Presto on Parquet files on S3, you will see that a lot of queries just return very fast because of the file format and various optimizations they know how to make. So on large amounts of data, it is actually going to sometimes be faster using the cold storage, using the right technology, than it's going to be using a document database of some sorts. In the case, for example, of Elasticsearch is probably going to be faster, but like I said, it will trade off precision with the speed. All right. Any other questions? All right. Thank you very much. I'll be here if you want to ask any questions.